Light with a wavelength of 200 nanometers strikes the surface of lead metal, ejecting an electron with a de Broglie wavelength of 0.9392 nanometers. So just to get a visualization of this, we have our photon, which is a particle of light, coming in, striking our lead metal, and an electron is being ejected. This is called the photoelectric effect. So we have an equation for this. E photon, so the energy of this photon, equals binding energy, the amount of energy that the metal is holding on to the electron, plus Ke, which is the kinetic energy of the ejected electron. So the excess energy from the photon goes to the kinetic energy of our ejected electron. So if we're trying to find the binding energy of lead in joules, I rearranged our equation so that we're solving for EB, binding energy. So EB equals E photon minus Ke. So let's use what we got. We're gonna find kinetic energy first. The equation for kinetic energy is half mu squared. The mass of the electron times the speed of the electron squared times a half. We have the mass, which is given 9.11 times 10 to the negative 31st kilograms, but what we don't have is the speed. What we have is de Broglie's wavelength, and that's the wavelength of matter, something with a mass. So the equation for de Broglie's wavelength is Planck's constant, so right here, Planck's constant, over the mass of the electron, in this case, times u, the velocity. So let's plug in what we know. We have the wavelength. It's in nanometers. 1 nanometer equals 1 times 10 to the negative 9 meters. Nine, 0.9392 times 10 to the negative 9 meters equals Planck's constant, 6.63 times 10 to the negative 39 joules times second, over the mass of the electron, 9.11 times 10 to the negative 31st kilograms times u. So if we solve for u should equal 774,884.67 meters per second. Now we have a u to plug in. So kinetic energy equals half the mass of the electron times our velocity of the electron that we just solved, meters per second, squared. So our kinetic energy is equal to 2.735 times 10 to the negative 19 joules. All right, so we have Ke. Now let's find E photon. So our equation for E photon is h, the same Planck's constant, times nu, which is frequency. Frequency is also equal to the speed of light over lambda, our wavelength. So if we were to write that into our equation, E photon equals Planck's constant times the speed of light times the wavelength, lambda. So our wavelength of this photon is right there, 200 nanometers. So let's plug it in. 6.63 times 10 to the negative 39 joules times second times our speed of light, 3 times 10 to the 8th meters per second, divided by our wavelength in meters. So 200 times 10 to the negative 9th meters. And that should give us an E photon of 9.945 times 10 to the negative 19 joules. All right, so we solved everything. We have E photon, we have our kinetic energy, so we do E photon minus our kinetic energy. That should give us a binding energy of 7.2 209 times 10 to the negative 19 joules.